Hello everyone. So today we will discuss about center of mass, which is again a very important concept when we are dealing with continuous distribution of bodies or discrete bodies, right? So let's say I have this object as shown by this blue line. As we can see, the shape of this object is a bit odd, and let's say this object is under the influence of forces F1, F2, F3, F4. Now, if we were to analyze the motion of this object in the existing configuration, then the analysis would become slightly tedious. Now, in order to simplify the analysis, we will assume that there is a point which exists, either inside the object or outside the object. So, in this case, let's assume that the point exists inside the object. We will call this point as this point as the center of mass, and we will assume that the entire mass of this object is concentrated at the center of mass, and all the forces which are acting on this object are essentially acting on the center of mass. So instead of analyzing this object, we will simply analyze the motion of the center of mass under the assumption that all the forces are acting on the center of mass only. So in a way, the center of mass is the geometric center of an object. Now let's understand how to find out that center of mass, right? So let's say I have this XY coordinate system, and in this coordinate system I have many small masses m1, m2, mi till mn. So for this system, let me find out the center of mass. So mathematically, the center of mass is defined as the following. So the x component of the center of mass is given by this formula, which is m1 times x1, which is mass of the first object, times the x coordinate of that object, plus m2 times x2 plus mn times xn divided by capital M, which essentially is summation of mi xi, I ranges from 1 to n, where n is the number of particles, divided by capital M. Similarly, y coordinate will be given by summation of mi yi divided by capital M. If we have a continuous mass distribution, then in that case the summation sign will be replaced by the integration sign. So the x component of the center of mass will be given by integration x dm by capital M, and the y component will be given by integration y dm by capital M. Now let's understand the principle of conservation of linear momentum. So first of all, let's understand what is linear momentum. So for a single object, its linear momentum is defined as its mass times its velocity. For a system of objects, the linear momentum of the system is defined as the summation of mass, or rather the summation of the linear momentum of all the individual objects in the system. Now we know by Newton's law that the net force acting on an object is equal to the mass times acceleration of the object, which is mass times, and acceleration is the rate of change of velocity, right? Now if we assume that the mass does not change with time, then I can write this equation as rate of change of mass times velocity. So force is equal to the rate of change of the momentum of the object. Similarly, for a system of objects, the net external force acting on the system will be given by the rate of change of the summation of the momentum of all the individual objects in the system by this equation, right? Now if the net external force acting on the system is 0, then by the rule of differentiation in this equation, this term will be constant, or rather the summation of the linear momentum of all the individual objects in the system will be constant. So this is the principle of conservation of linear momentum. It states that if the net external force acting on a system of objects is 0, then the linear momentum of the system of objects remains constant, or the linear momentum of the system remains conserved. So thanks for watching this video. In the next video, we will see the application of this principle of conservation of linear momentum in the rocket propulsion. So if you have liked this video, then please do subscribe to my channel. Thank you.